we've covered all the forms of energy that we need to cover for this class, ME 2134 thermodynamics. So I'd like to give you some examples of how we could transform one form of energy into another before we get into the nitty-gritty details of what we're going to call the energy balance, or in other words, the first law of thermodynamics. So let's go through some examples first. Let's refresh your memory on what we've covered. We've covered two categories of energy, haven't we? So let's cover the most recent boundary phenomena, things that are only identified as the energy crosses the system boundary. Heat added to the system, I'm going to say QN. Use QN, not just Q. And work done by the system. Call that W out, not just W. Now, remember that a system cannot possess heat and it doesn't possess work. These forms of energy only occur as they cross the system boundary. But things that the closed system does possess are these forms of energy. Internal energy, capital U, might be a little new to you, but we've defined it. Kinetic energy, not new to you. You covered in high school physics. Kinetic energy, property of the system. Potential energy, not new to you, covered in high school physics. And here's our sketch, just as a reminder, right? So we've got our tried and true piston and cylinder. Not everything is a piston and cylinder, but it's just sort of a great example problem. Here's our closed system in the red dashed line. We've got Q in crossing the system boundary, W out crossing the system boundary. And we're depicting here on the sketch that we're moving from state one to state two in some process. All right, so that's our setup. You're good with all that. So what I'd like to do is go through some easy examples first. So I'm going to claim that it's easy to transform work into heat. That's an easy task. I'm going to suggest that it's a little harder to transform heat into work. So let's go with the easy stuff first. Okay. An easy example of transforming work into heat. Now, when you just run the PowerPoint on its own, this cartoon fellow, he is walking across the floor, and how many times have you felt like this? I felt like this many times. And he is dragging instead of picking his feet up, he's dragging his feet across the floor as he's walking. I mean, he's tired. He's just dragging those feet. And so he's really shuffling. And so here's, how many times have our parents told us to stop shuffling? Well, I got that treatment a lot when I was a lot younger. So dragging or shuffling your feet across the floor, I think, is a great example of a way to turn work into heat. What are you doing when you're shuffling or you're moving your shoes against the ground? You're doing work, aren't you? You're moving a force through a distance. Whether you like it or not, it makes you even more tired because you're expending work, you're doing work to drag your feet across the floor. And if you drag them enough, you can probably feel that the soles of your feet are getting warmer. You're transforming the work you're doing into heat, and to some extent, you're warming up the carpet as you're dragging those feet across the carpet. And so, back to thermodynamics, yeah, you've got a feel for it. Common sense gives you a feel for that. So back to thermodynamics, any process that involves friction results in some measure of transforming work, a force through a distance, into heat. So that's my classic example of turning work into heat. Now, here's another one. Do you remember that we mentioned that electricity is considered, for this class, doing work? It has the ability to do work. Remember the example of hooking electricity up to an electric motor and lifting a weight. Well, here's a classic way to turn electric power or electric energy into heat immediately without lifting a weight, an electric baseboard heater or a space heater. Now, it turns out that if you need to heat your house or you need to heat even just a room or a local area, it's pretty in the whole scheme of things, it's pretty inexpensive to buy a space heater or buy a number of baseboard heaters for your different rooms and plug them in, and you'll find that you can heat your house or your heat up your local room pretty quickly and pretty inexpensively from an install cost. It doesn't cost much to buy these pieces of equipment. You do have to buy the electric power, don't you? But that's a whole nother story. But this is an easy way to transform work, electric energy, into heat. Easy. This was one of my proudest images. When I came back to teach thermo class after I retired in 2019, I was so proud of finding this image because it illustrates how you can turn work, electric energy, into heat. Uh, and back then, old school incandescent light bulbs were more prevalent than they are now. And gosh, that was only about 5 years ago. But you get the point. So you know what an old incandescent light bulb is made of. Essentially, you get a source of electric power, you hook your light bulb up, and isn't that filament? That a filament is essentially a resistor. That's all it is. It's an electric resistance resistor, and there is so much energy dropped across that resistor that the tungsten element gets very hot, and that's what gives you the lumens for your light. So remember that the light bulb wasn't invented until about 1900. It's hard to believe. And then, of course, nowadays, you get a lot more bang for your buck. It doesn't take nearly as much electricity to run an LED light strip, and it doesn't heat up nearly as much. But of course, you get the idea. There is some heating, of course, even with a current day LED light strip. All right, so what are we doing? We're examples of easy ways to transform work into heat. Okay, now a little harder. It's a little harder to transform heat into work. All right, so here's my example. So I'm just going to do a on paper example and then get to the real world here in a second. Here's our tried and true piston and cylinder closed system. It's a gas here at state one. And what we're going to do is we're going to add heat to this system, Qn greater than 0. We're going to add heat. And we're going to add enough heat so that we go through a process so that the system expands, does some work, of course, and expands to state 2. Okay. Do you see that what you've done in this proposed process, you have added heat and you've gotten out some work? And so in my example, I'm saying, look, this is a way to transform heat into work. Does that kind of make sense? Is that a decent example for you? So adding heat to the closed system causes the gas to expand and move the piston through a distance. And so there's some measure of transforming heat into work. Now I'm going to go back. It's so neat to reflect back about history and engineering and invention in history. And here is an example of transforming heat into work, and it's the real world steam engine. And when you look at my slide, so you see that, of course, there are very few, only for visitors and for fun and excursions and tourists and entertainment do steam locomotives still exist. So there still are, a number of steam locomotives still in existence. Nowadays, trains, locomotives are powered by diesel engines. But back in the day, and in fact, I strongly recommend that you visit, as a mechanical engineer, visit Wikipedia, look up the Industrial Revolution, and you'll learn that the Industrial Revolution it started around 1760 in Great Britain. I think the name was Watt. Um, is a He was an inventor, and he figured out a way to transform heat into work, and that hadn't been figured out to do that functionally since before that. So here's our steam engine, and of course, you see what's going on there. But this cutaway I was able to find, and you see that there are multiple pieces of equipment involved in the old school steam engine locomotive. There's a boiler. Okay, so there's a boiler in which we're adding heat and we're generating steam. And this purple would sort of be the supply steam. That supply steam goes to the good old piston and cylinder that through mechanical engineering linkages drive the drive the wheels of the locomotive, and that's what, of course, propels the locomotive and its load down the tracks. You folks know that, but extraordinarily interesting history of mechanical engineering that didn't start around 1760. And boy, this was a world-changing transformation, wasn't it? If you think about history before the Industrial Revolution and then during and after the Industrial Revolution, and you think about uh, additional inform the additional innovations that have come as a result of this invention, the steam engine, it just blows your mind. It blows my mind. And so you'll notice here that I make the green text box remark, the steam engine has transformed the world. So strongly recommend as a young engineer, go to Wikipedia and read up a little bit about the Industrial Revolution. Okay, so those were my examples of transforming work into heat, easy, and heat into work, harder. And now I want to give some examples of transforming boundary phenomena, let's say heat in or work out, into internal energy. So that's another transformation that I want to give you some examples about. Okay, so let's look at my example. I want to compress the gas in a piston and cylinder situation. So you have to use your imagination. We're going to start out here at state one, where we've got this high volume of gas contained in a piston and cylinder. Now, I've added something to this tried and true sketch, haven't I? I'm depicting the surroundings, the cylinder wall with this crosshatched drawing. That's insulation. So, for example, what I'm going to suggest is I want to fully insulate the piston and cylinder from the surroundings. And so you get the idea. So do you see how I've tried to depict this plain old block of styrofoam, right? And so I'm just imagining that I could take some styrofoam and wrap it around the cylinder wall. And now some very smart students would say, now, wait a minute, you know that there is some substance associated with the styrofoam, so there will be some thermal communication between the cylinder wall and the surroundings. Now, I do agree to some extent that's true, but just imagine in your mind that we've got so much styrofoam insulation there that we have prevented heat transfer from the cylinder wall to the surroundings. So just kind of go with me on that. And in my sketch, I'm showing Qn equals 0. So I'm going to move my piston down. I'm going to have some force. I'm going to admit some force, some heavier force down on the piston, and I'm going to compress the gas in the closed system so that W out is less than 0. So do you see that W out is not a positive number, it's a negative number. I'm pushing down on the system. So even though I'm showing W out with my red arrow going out, I am also depicting in my sketch W out is less than 0. That's important. And so the question to you is, what do you figure if I compress the gas in this insulated piston and cylinder, what do you figure is going to happen to the internal energy of the closed system? You think about that a second. I'm squashing that down. I've insulated the cylinder wall. What do you think is going to happen? In your experience, do you have anything that you can relate in your experience to something like this? How about pumping up the pressure in your tires with a hand pump that's got the handle on it that you're pushing down and then you're returning and you push down again? Have you ever felt that air pump after you finished increasing the pressure in your tires? The cylinder, the piston and cylinder that you're using, it gets hot. Okay. And so that's the real world example of doing work on a piston and cylinder. And what's that air inside in there, it gets hot. Okay. And that's what you're pushing into your bicycle tire. So anyway, the right answer is I would expect the internal energy of this closed system to go up if I do work on the closed system. So anyway, that's about the best I can do to talk about doing work and increase the internal energy of a system. Just an example to kind of get you set up for our next video. Another example, we've got a rigid vessel. And so do you see here in my sketch, I'm showing a rigid vessel. It's not a piston and cylinder. It's just a rigid vessel, like a closed tank. And my closed system is the dashed line that I'm showing. And of course, do you see that if you go through some process involving a rigid tank, and all we're doing is we're going to light a flame, okay, underneath this rigid tank, might be made of steel. We're going to add heat to the closed system. So in my sketch, I'm showing Q in greater than 0 with my arrow going in. Okay. What's the work done by the closed system for this process? Work done. Integral P dV. What's dV? What's the change in volume, even the increment in dV, incremental change in volume of this tank? It's nothing. And so the integral P dV is 0. So I've labeled workout as 0. All right, well, let's go through the mental exercise of this situation where we're adding heat to the tank. It's a rigid vessel. What do you figure will happen to the internal energy U of the closed system? Well, I think the internal energy is going to go up because you see how we're sort of transforming this type of energy into internal energy. It's a transformation process. Now, common sense 101. What do you figure is going to happen to the temperature of this gas in here? I figure it's going to go up. What do you figure is going to happen to the pressure in this tank as you heat this rigid vessel? My intuition tells me the pressure is going to go up too. Now, you're going to be able to show it. In a couple of weeks, you're going to be able to quantify this. You're going to be able to show this, yes. What will happen to the specific volume in the tank? This is like a little quiz question that might appear on a quiz. What's going to happen to the specific volume V? Anybody? Well, I wish there was somebody on the call here to volunteer up that the specific volume, definition of specific volume, it's capital V divided by M. How's capital V changing here? It's not. It's constant. How about the mass? Is the mass changing? No. V over M is constant. And so for this proposed process, the specific volume of the tank contents doesn't change. Okay. So quick answers. What's going to happen to the internal energy? Increase. Temperature. Increase. Pressure. Increase. Specific volume. Stay the same. Okay, we've reached our examples of transforming forms of energy from one to another. And so what did we learn? What's the recap from this video? Well, there are various forms of energy, and they can be categorized into boundary phenomena, heat transfer and work, or system properties, internal energy, kinetic energy, potential energy. We have visualized some examples of ways that one form of energy can be transformed into another. So I hope that it sort of helps get you ready of thinking about energy forms. Okay. I've tried to show you that some transformations are easier than others. That could not be more true. And that's why mechanical engineers make the big bucks. Common sense 101 is usually your friend. And so when you're reading problems and trying to scope out what are you going to do, where am I going to start? After I've started with the sketch, now where do I start? sometimes Common Sense 101 can at least help guide you into where you're going to go, or at least um, guide you in terms of what kind of numerical results you should get. And so never discount your Common Sense 101 when you're solving these problems. So those are my examples. In the next video, we're going to introduce the first law of thermodynamics. And this is that will be sort of an exciting fundamental principle that you're going to be using throughout the rest of the course, all the way to the last day of the course, and then into your next set of classes in mechanical engineering till you graduate. And then you're still going to be using the first law of thermodynamics beyond that in your engineering practice. So it's going to be kind of exciting, maybe more exciting for me than for you because I've passed the class. But I hope that you're going to get some understanding as a result of the videos when I try to introduce the first law of thermodynamics to you in the next video.